Okay, CLISI 10. So we want to compute a line integral. We've got a vector field given to us. Tragically, we don't have a curve explicitly given. We're only told that the curve C starts at a certain point and ends at a certain point. Now, if there's no curve given, we have to use a little bit of mathematical, sort of non-mathematical reasoning here and ask, well, how could this problem be a well-posed problem? There's no curve. Oh, maybe the curve doesn't matter. It's possible this might be path independent, in which case this does become a well-posed problem. Does that make sense? Yeah. So now that doesn't prove the problem's path independent. All it shows is that if this vector field is not path independent, then whoever wrote this problem messed up. Wrote a bad problem. So we are strongly suspicious that this vector field is path independent. We check that by taking this vector field and computing its curl. And if you compute the curl of this thing, let's see, well, yeah, I claim it's 0. Let's see here. The first component is 0. The second component, let's see, 2. Yeah, second component is 0. And third component, yep, also 0. So that means that this is a path-independent vector field, and so all of a sudden the problem at least makes sense. So the problem is that, again, we're looking at some curve that starts there and ends here, and I don't know what that curve is. It might go around and do that, or it might just be a straight line path like that. Not sure. Doesn't matter though. Beautifully. So one thing you could do at this point is just parameterize your favorite path from the origin to that point. I assume the straight line path is probably your favorite. It's my favorite path. And use Chapter 5 techniques. That would be one thing to do. Now, option 2. Since it's path independent, because the curl is 0, you know that this vector field has an anti-gradient. Right? And you could try to apply the fundamental thermal line integrals, and that's what I think is probably the best thing to do. Take this vector field and find an anti-gradient. So the function f would have to equal to each of the following 3 things. It would have to be, first of all, I take the x anti-partial of that first term, and that's going to be x squared e to the yz, possibly plus some constant function of y and z. Okay, now it's also got to equal to the y anti-partial of that second term, and the y anti-partial, it's x squared e to the yz. So how about that? That's cool. Now, again, plus possibly some function of x and z. Now the z anti-partial of that third term, well, what are the odds? X squared e to the yz. So we don't even have to do any mixing and matching. It's just, that's it. All right, so you've got your anti-gradient. The line integral problem over this unknown curve then becomes a line integral of the gradient of f, because we've successfully found that anti-gradient, which means I can rewrite this as just f of b minus f of a. There's f. That's the 420 point. That's the origin. Plug in arithmetic. Yeah. So it's a little easier than parameterizing the path, I think. But that wouldn't be bad to parameterize the path. It would be...
So if you try to find the anti-gradient, you couldn't quite get it, then you could...
Yeah, I mean, if for whatever reason, if you just don't like anti-gradient, or if as you're trying to find the anti-gradient, you're noticing, oh my gosh, okay, how do I take the antiderivative of that thing? Then you might try the parameterizing. Now, the catch on the parameterizing is, of course, you're still going to have to compute an integral, and that integral is still going to involve that vector field. It's just that you're going to plug stuff in, formulas for x, y, and z, but you just might find that a little bit friendlier somehow. They're antiderivatives instead of anti-partial derivatives. And if, so if for whatever reason, if you want to, it's perfectly fine. Yep. That makes sense?
Yeah.
Everybody good?
I wasn't listening.
Oh, okay. All right. Okay. All right.